Dear students, I, Mr. Vishal Shah, Assistant Professor, Krishna Institute of Pharmacy, Karad, once again welcome you all to this my YouTube channel. In this video, we are going to discuss about the another major part of this chapter, that is the cycloalkanes. Previously, we have covered with the methods of preparation, chemical properties of cycloalkanes. Now, if you have not gone through these videos, you can just check YouTube channel, go through these videos, and if you like the content of this channel, then you can subscribe to my YouTube channel. Now, in this video, we are going to discuss about the conformations of the cycloalkanes. Basically, we will be dealing or we will be studying the conformations of cycloalkanes with respect to cyclohexane. So let's start with our today's session. Now, before proceeding towards our session, just we will see the learning outcomes of this session. After this session, students will be able to explain the conformations of the cyclohexanes. So let's begin with conformations of cycloalkanes. Now let me tell you what is the meaning of conformation. Now, if a single bonded molecule is there between carbon-carbon atoms, so this single bond or that molecule can be rotated by 360 degree along that particular bond, and whatever the different positions that we are getting by rotation of that single covalent bond and whatever the different structures that are generated, these are nothing but the conformations of that particular compound. So n number of conformations can be drawn for a single molecule, but out of that only few are stable and which can exist, which can be isolated in the nature. So they are known as the conformations. So for cycloalkanes also various conformations that are possible. So that we are going to study in this particular video. Now in this part we are specially dealing with the cyclohexane because of its special importance. We will proceed to smaller rings and then give a brief exposition of the conformations of larger rings. Now you can assume that if the carbon of cyclohexane ring were placed at the corners of regular planar hexagon like a benzene structure, all the carbon-carbon-carbon bond angles would have to be 120 degrees Celsius. Means as cyclohexane ring is having 6 carbon atoms, and if these all 6 carbon atoms, if they are placed at the corner of hexagon, then carbon-carbon bond angle would become the 120 degrees Celsius. Now, because the expected normal carbon-carbon bond angle should be near to the tetrahedral value, because we know that the tetrahedral bond, when carbon is present in the sp3 hybridized state, it shows tetrahedral geometry with an bond angle of 109.5 degrees. But here, because the expected normal value of tetrahedral carbon atom is 109 degree, the suggested planar configuration of cyclohexane would have angle strain. Means by placing or by drawing the cyclohexane structure by using this method, we are getting a bond angle of 120, but suggested bond angle is 109. If this is the situation, then cyclohexane ring would have an angle strain at each carbon atom and would correspond to the less stable cyclohexane molecule than those with more bond angles. If this tetrahedral geometry is not maintained, then that particular bond angle would become unstable. So this will also happen in case of the cyclohexane. The actual normal value for the carbon-carbon-carbon bond angle of the open chain carbon unit appears to be 112.5 degree, which is 3 degree greater as compared to the tetrahedral value. From this we can conclude that the angle strain at each carbon of planar ring would be 120 degree minus 112.5 7.5 degree, that is equal to 7.5 degree. So 7.5 degree is angle strain that is present on that particular each carbon atom. Angle strain is not the whole story with regard to the instability of the planar form, because in addition to that, having carbon-carbon-carbon bond angle different from their normal values, the planar structure also has its carbons, hydrogens, which are in the unfavorable equilibrium arrangement. Means angle strain means what? When the geometry is having sp3 hybridized state, and if the bond angle is not maintained, the whatever the bond lengths are there, these bond lengths become curved to maintain that particular bond angle, and in such a case they will feel certain strain on that particular bond length, on that particular, due to which carbon atoms that are involved in that bond length, they will feel some type of force, and that force is known as the strain, angle strain. If this angle strain is more, then the instability of that ring will be more. If this angle strain is less, then instability will be less. So here only angle strain is not the way by which we can calculate the instability of the planar ring, but in addition to that, the planar structure of its carbon and hydrogen which are present in the unfavorable eclipsed arrangement, which is also accountable for the instability of that particular planar ring. If the carbon valence angles are kept near the tetrahedral value, you will find that you can construct ball and stick models of cyclohexane with the 6 carbon atoms that are present in the ring with 2 different conformations. And these conformations are known as chair and boat conformations. Here I have shown you, this is the chair conformation, this is the boat conformation. Now why they are known as the chair conformation and boat conformation? If you look at this particular structure, it looks like a chair. Here you can see 6 carbon atoms are placed. Now when cyclohexane molecule, as it is an aliphatic compound, it is a planar structure. If we represent it like the benzene ring, then bond angle will become the 120. But actually, if 120 bond angle is there, then that particular ring must have a strain. And to relieve this particular strain, cyclohexane molecule, means whatever the carbon atoms that are involved in the cyclohexane molecule, they rearrange itself in such a way that they will look like this. Here you can see 6 carbon atoms are placed. Each carbon atom is having 2 types of hydrogen. These red hydrogens, they are known as the equatorials, and they are these blue hydrogens, they are known as the axial. These are red are known as the axial, and these blue are known as the equatorial. So in this way, 2 different types of hydrogens that are present in this particular cyclohexane molecule. By rotating first and fourth carbon atom, this chair form can be converted into the boat form. So here you can see this is the shape like a boat, that's why they are known as the boat conformation. Now whatever hydrogens that are present in the axial position in this structure, they become equatorial in this particular boat conformation. In this way, change in the conformation of that cyclohexane is observed. Means 2 conformations that are possible, which are broadly considered, they are known as the chair conformation and boat conformation. So many conformations are there for cyclohexane, but here we are only considering 2 which are mostly available. It has not been possible to separate cyclohexane at room temperature into pure isomeric forms, that is the boat form or the chair form, that correspond to this conformation. And actually the 2 forms appear to be rapidly interconverted. The chair conformation is considerably more stable, and it comprises more than 99.9% of the equilibrium mixture at room temperature, because chair conformation is nothing but the trans conformation, where the weight of these carbon atoms is balanced on both the sides. That's why they are more stable as compared to the boat conformation. The boat form is less stable as compared to the chair form, and mostly 99.99% of cyclohexane exists in the chair form. Only less than 0.1% is available in the boat form. The reason is that the boat form has unfavorable non-bonded interactions between the hydrogen atoms around the ring, and due to which they are unstable. If we make all of the bond angles normal and orient the carbons to give the extreme boat conformation, a pair of 1,4 hydrogens, they are known as the flagpole hydrogens, have to be very close together. Hydrogens this close together would be on the rising part of the repulsion potential energy curve for hydrogen-hydrogen non-bonded interaction. And due to this steric hindrance at hydrogen-hydrogen distance of 1.8 correspond to the repulsion energy of about 3 kilocalorie per mole. Means the flagpole hydrogens means hydrogen atoms that are present at the first and fourth carbon atom. If they come more closer towards each other at the bond length 1.83 angstrom, then due to the steric hindrance between hydrogen-hydrogen, repulsion force will be existing, and due to this repulsion, that molecule becomes unstable by 3 kilocalorie per mole energy. There is still another factor that makes the extreme boat form unfavorable, namely that the 8 hydrogen along the sides of the boat are eclipsed, which brings them substantially closer together than they would be in the staggered arrangement, and due to which boat conformations are less stable. This is in striking contrast with the chair form, from which adjacent hydrogens are in staggered position with respect to one another all around the ring. Therefore, chair form is expected to be more stable as compared to the boat form because it has less repulsion between the hydrogen. Means in case of boat conformation, 8 hydrogen atoms are being closer towards each other, and they exist in the eclipsed as well as the staggered conformation, and due to the repulsion between the like atoms, the energy of that molecule will be more, and as energy of that molecule will be more, then it becomes less stable as compared to the chair conformation. Chair conformation is considered as a more stable. The chair structure is quite rigid, and the rotation does not occur around the carbon-carbon bond with interconversion to the boat structure. In contrast, the boat form is quite flexible, and due to which it is more unstable. Rotation about carbon-carbon bond permits the ring to twist one way or the other from the extreme boat conformation to considerably more stable equal energy conformations, in which the flagpole hydrogens move further apart and the 8 hydrogens along the side becomes largely but not completely staggered. These arrangements are called as the twisted boat. This is the another conformation that is possible for the cycloalkane, which is known as the twist boat conformation, and they are believed to be about 5 kilocalorie per mole less stable as compared to the chair form. Means chair form is more stable. The boat conformation is less stable by 3 kilocalorie per mole, and another conformation, that is the twist boat, which is less stable by 5 kilocalorie per mole as compared to the chair. Further, anti-boat conformation is also possible for cyclohexane, which is less stable as compared to the all other conformation of cyclohexane. So this is about the conformation of cyclohexane. Here just we have to remember that two major conformations are possible. One is the chair conformation and other is the boat conformation. Out of this, chair conformation is more stable as compared to the boat conformation. So thank you.